The moment you've been waiting for, everybody. Class recording has started. So, last week, when we were first introducing this idea of force, we talked about these four fundamental forces in the universe, and one of them was gravity. And we talked about some things that affect gravity. First off, we know that gravity, that part in yellow is going to come in here handy in a second, so don't write that down just yet. Let's see if I can do this. Oh, look at that. All right, so gravity is an attractive force that exists between any two objects. Gravity, an attractive force that exists between any two objects. And last week, we talked about some of the factors that influence how much gravity there is, like the amount of mass that these two objects have. And there's a direct relationship there between the amount of mass that two objects have and how much gravity is between them. And then distance is an inverse relationship. But remember that we talked about that it's not just an inverse relationship, it's actually an inverse square relationship. Remember that we had this set up where if this was the force of gravity that exists between two objects, that we said that it's equal to 1 over d for the distance. But remember, it's not just d, it's d squared.
We didn't talk about this?
No, I think we did.
We didn't talk about this.
Totally talked about this. As a matter of fact, I think I recorded class when we talked about it, so we can check that recording.
Was this like a long time ago?
It was last Monday, and we didn't talk about it real long, but we did talk about
Oh, yeah, we
it.
did.
So.
Beats
All right.
me.
It does end up being like a parabola. It's actually not so much like a parabola. It's more kind of like this. Like it starts high and goes low like this, but steeper than an inverse relationship. Hey, this doesn't require conversations. Hey, do that on your own time. Just because you didn't do it for homework this weekend doesn't mean you can do it now. All right. So that's gravity. Now, we generally think of gravity as gravity here on Earth. And yes, that's true. Yeah, it's too high and too loud. But it's not that hot.
Maddie just turned the fan.
Well, the windows then, because there's lots of cold air outside. Well, if it's hot, you can come sit up here if you want.
What?
All right, but turn the fan on. All right. I'm glad we're recording class today. All these nice distractions. Thanks, everybody. All right. So we generally think of gravity as gravity here on Earth, and yes, there is gravity here on Earth, but that doesn't mean it's any different than any other gravity. For instance, gravity on Earth pulls things towards its center, just like any kind of gravity does. Gravity is an attractive force. It pulls things together. And because gravity is acting on something, it can cause changes in motion. Like what? What kind of changes in motion could it occur? Or could it cause? Speeding up, slowing down, and changing direction, right? We've talked on several occasions about me taking this ball, throwing it up into the air, and catching it again, right? All three of those things happen. It slows down on the way up, it changes directions up at the top, it speeds up on the way back down. So Earth's gravity will cause that to happen. Now, one of the reasons why we think of Earth's gravity as being this super important idea or super important thing is because two reasons. One, Earth has a real large mass, at least very large compared to us. Second, we are really, really close to Earth, and therefore those two factors make it seem like Earth's gravity is something special. But in reality, it's just like any other gravity, or any force for that matter. It does the thing forces do. It does the stuff gravity does. But because of where we are located, so close to the Earth, we do need to take into account Earth's gravity when we are influencing the effect of motion, whether it's sideways, up and down, whatever it might be, because it plays such a large role in what we do. Okay? All right. Remember units threw a bunch of new words at you, new vocabulary words, and some of them like sounded like words you knew what they already knew what they meant, but really they meant something different, and that caused a lot of you to be confused. Here we go. This unit, we have a couple of those things, like these two words, mass and weight. First, we've introduced this idea of mass before. What does the mass of an object tell you? Sorry, go ahead. The amount of matter it has, and that's true. We also said it tells you something else about its motion. What else does mass tell you about its motion? Anybody remember? That means that it has more.
I said it. Ish.
Mass tells you how much inertia something has, right? So it's not necessarily how much harder it is for it to move, but how hard it is to change. So mass tells you how much stuff is there, how much matter is there, but it also tells you how much inertia something has. Is that going to change regardless of what's around this object? No, that stays exactly the same. Mass does not change regardless of location. How many atoms make me up doesn't change if I'm here, or if I'm on the moon, or if I go to the sun, or any of those other things. And that means that I have just as much inertia here as I do on the moon, or as I do on the sun, but that means it's just as hard for me to get moving, or start moving, stop moving, any of those things inertia covers anywhere in the universe.
To measure the object's inertia, then does it like the gravity acting on
Now, that's different though, Becca, because gravity is a what?
force?
A force, right?
But can't that, for inertia, the object wants to keep on going in whatever direction or whatever state it's in, and then if like
It's not, so Becca, it's the difference between this. Will you come and stand right here for me? It's the difference between me throwing it this hard, okay, or me throwing it this hard, okay? Is there anything different about the ball
no.
from the way I throw it? What was different from throw one to throw two?
The
The
amount of force.
amount of force I apply, and therefore there is a difference in the acceleration of that object,
Okay.
but not anything different in the object itself. Does that make sense?
Yes.
Okay? And that's mass. That's not going to change regardless of where we are. Okay? But, and Becca, this is a good transition, okay? But weight, on the other hand, is defined as the force of gravity that exists on an object. The weight of the object is the force of gravity that exists on it. Now, we just discussed what are some of the factors that affect the force of gravity acting on an object. No, that's what something does in response to gravity. What affects how much gravity is acting on an object? Mass and look about 4 lines up on your paper. And distance, how far apart they are. Okay? Those 2 factors therefore affect how much weight an object has. The amount of gravity or the weight of an object can be determined by or affected by the mass of that object and the acceleration caused by gravity. I realize the space isn't quite big enough to fit all that there. Just use some space underneath it. So the amount of gravity, or the weight of an object, depends on its mass and the acceleration caused by gravity at whatever location it's in, which takes into account that whole distance idea. It also takes into account the mass of the other object, whether it's the Earth or the moon or whatever it might be. So don't think that this contradicts what you wrote earlier in your outline. It's just a different way of stating the same thing. Maddie, go ahead.
So if someone was at rest, then their acceleration would be 0 and it would only depend on mass?
Okay, that's a good, Maddie, that is a great question, okay? Because, so let's draw a picture, okay? So here's my object.
Question.
Maddie's, the,
I asked if the acceleration was 0 if it was like at rest.
let me restate it so that so that the recording can hear it too. So Maddie asks, if the object is at rest, that means that its acceleration is 0. Therefore, if we just learned if the weight depends on the mass and the acceleration caused by gravity. So if the acceleration of the object is 0, does that mean it only depends on mass? And the answer is no. Because weight is a specific force, right, Maddie? It's the force of what?
Mass and direction.
No. It's the force of what? Gravity. So if we go back to this picture, I would draw an arrow like this. Okay? This is, oh, not blue, yikes. This is the force of gravity. This would be the weight. Okay? If no other forces were acting on that object, what would happen to it? It would fall, right? And here on Earth, we know that it falls and that its acceleration is what? 9.81, or pretty close to 10. Right? Because it's supposed to be squiggly. Okay? Maddie, this is the acceleration caused by gravity. Okay? That doesn't change. But the acceleration of this ball might change, not because gravity changes, but because why? How do I get the acceleration of this ball or the motion of this ball to be different than it is now? Apply another force. Does that make sense? That if gravity and only gravity are acting on this object, it has an acceleration of 10 or close to it. And that's the acceleration of gravity. Not necessarily the acceleration of that object, because we have to take a look at the other forces. Does that make sense? So just because an object may be at rest doesn't mean that it doesn't have weight. It still has a force of gravity acting on it. It just so happens that that force of gravity happens to be balanced out by a different force. But that doesn't change the fact that gravity is still acting on it. Is that good? Okay? All right. So taking that into account, we can figure out how much force gravity is acting on it by using this formula. And this formula, there isn't a place for you to write this on your outline, so you may have to write it on the left-hand side. Sorry, I changed some things this morning because I like this better. So, F of G, the force caused by gravity, is equal to M times G, where M is the mass of whatever object we're talking about, and G is the acceleration caused by gravity at whatever location we're at. And we know here on Earth that acceleration is real close to 10. So the force of gravity acting on an object is equal to M times G, where M is the mass of that object, and G is the acceleration caused by gravity at that location. That good for now? So going back to this picture, let's say this object has a mass of 5 kilograms, okay? Could we figure out how much gravity is acting on it, right? We just learned that the force of gravity on something, or its weight, is equal to M times G. So if we plug 5 in for m, and g we know is pretty close to 10, right? The force of gravity, or the weight of this object, is 50 newtons. Okay, now that formula is used and get you in newtons. Okay, it won't give you pounds, but it will give you newtons. Now, that 50 newtons is always going to be acting on it. But if we apply another force that's 50 newtons this way, what's that object going to do?
Be at rest.
Whatever it's doing right now, right? That might be at rest, but it also could be what?
Traveling constant.
Constant speed or constant velocity. Okay. Does that make sense? All right, this next slide that I'm going to show you, once again, it's not written down on your sheet, but this has test question written all over it. All right. So this has like short answer question written all over it. All right. So do objects weigh more on the moon or more on Earth? Nope. Do objects weigh more on the moon, or do they weigh more on Earth? They weigh more on Earth. Why?
The force of gravity is
The
more.
force of gravity is greater on Earth than it is on the moon, because the Earth has a bigger mass. But do objects have more mass on the moon or on the Earth? Same. The answer is they're the same. The amount of mass something has doesn't depend on what location it's in. But the force of gravity will depend on what location it's in. This has like short answer question written all over it. All right. Next, I want you to watch a little video. This video is 2 minutes and 5 seconds long, and it deals with objects that fall. So hence the name of it is, I'll show you in a second here. Hence the name of it is falling objects. Okay? So, I'll play this for you here, and we'll discuss. 2 minutes, 5 seconds. Ready? Go. Or not. Come on, falling objects. There we go. Okay, here we go. Oh,
In this demonstration, we're going to show
sorry. At the end of the video, I'm going to do something up here in the front that I want you to compare with what's going on in the video. It's kind of like me being inserted into the video. Alright? So, sorry to interrupt your viewing, but here we go. Okay. Come on.
In this demonstration, we're going to show the effect of air resistance. If we drop a penny and a feather in a chamber filled with air, they do just as we expect. The penny hits first and the feather falls later. This is because the feather was playing the role of an airplane. It was floating on a cushion of air, like a parachute. But if we remove the air from the chamber, in effect making it a vacuum, then we get something entirely different. When we drop the penny and the feather this time, you see that they fall neck and neck simultaneously, and they both will hit the ground at the same time. All objects, no matter how big, how small, how light or heavy, will increase in speed as they fall, gaining 32 feet per second each second. If we slow this down, we can see the penny and the feather side by side, both increasing in speed together, and both reaching the bottom of the chamber at the same time. This is the law of falling objects. Once again, it doesn't make any difference how big or how small the object is. If we neglect the effect of the air, they all fall at the same rate. When astronaut David Scott on Apollo 15 walked on the moon, he thought that this would be an excellent demonstration to show.
Well, in my left hand I have a feather. In my right hand a hammer. I guess one of the reasons we got here today was because of the gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And I'll drop the two up here and hopefully they'll hit the ground at the same time.
tomorrow we will discuss this video and carry on with why gravity does what you just saw happen in the video.